The James Webb Space Telescope, NASA's crown jewel in modern astronomy, has solidified its position as the most advanced observatory in the field of space science. Its mission, vast and profound, is to unravel the mysteries that lie both within our solar system and across the far reaches of the cosmos. With its unmatched sensitivity and resolution, Webb is illuminating the dark corners of the universe and redefining humanity's understanding of the celestial tapestry we are a part of. Recently, scientists aimed this extraordinary instrument toward a star located approximately 120 light-years from Earth, and what they uncovered has sent ripples through the global astronomical community. The target, a world known as K2-18b, an exoplanet believed to harbor characteristics that place it among the most compelling candidates in the ongoing search for life beyond Earth. In a groundbreaking revelation, Webb detected clear signs of carbon-based molecules, methane and carbon dioxide, within this planet's atmosphere, hinting strongly at the possibility that this distant orb may host a global ocean beneath a hydrogen-rich shroud. The implications of this discovery are staggering, for it offers a glimpse into a planetary system utterly unlike anything within our own solar backyard, raising exciting questions about habitability in the wider universe. K2-18b, orbiting a cool red dwarf star in the constellation Leo, lies firmly within what scientists refer to as the habitable zone, the region around a star where conditions could permit the presence of liquid water on a planet's surface. This particular exoplanet boasts a mass approximately 8.6 times that of Earth and a radius about 2.6 times larger, placing it in the category of subneptunes, a class of planets absent from our solar system but commonly found elsewhere in the galaxy. Previous observations by NASA's Hubble Space Telescope had already hinted at the presence of a hydrogen-rich atmosphere, but Webb's powerful infrared instruments have now confirmed the atmospheric composition with far greater clarity. The discovery of both methane and carbon dioxide, coupled with the apparent absence of ammonia, supports a tantalizing hypothesis. K2-18b could possess an ocean beneath its thick atmosphere, potentially making it a viable environment for life as we understand it. Adding another layer of intrigue is the possible detection of dimethyl sulfide, or DMS, a molecule that on Earth is exclusively produced by biological processes, particularly by marine phytoplankton. While Webb's current data is not sufficient to confirm the presence of DMS with certainty, its potential existence within K2-18b's atmospheric profile has sparked an urgent call for follow-up observations to verify this potentially biosignature-defining compound. The team responsible for these observations emphasized the need for caution, noting that even though K2-18b lies in a habitable zone and shows strong signs of carbon compounds, this does not necessarily confirm the presence of life. According to researchers at the University of Cambridge, the planet's substantial size and mass suggest that it is likely composed of a dense core, possibly enveloped by a high-pressure mantle of ice reminiscent of Neptune. Above this icy layer may lie a thinner hydrogen-dominated atmosphere with a global ocean interface between the two. The presence of water alone, while essential, is not sufficient for life to emerge or thrive. There remain questions about the ocean's temperature, chemical balance, and structural dynamics, whether it is a free-flowing sea or a rigid, pressurized brine locked beneath layers of ice. Regardless of the uncertainty, Webb has provided the most detailed atmospheric spectrum of a habitable zone subneptune to date, marking an extraordinary leap forward in exoplanetary science. By analyzing the starlight filtering through K2-18b's atmosphere as the planet transits its host star, astronomers were able to identify specific molecular fingerprints that pointed to the planet's chemical composition. This method, known as transmission spectroscopy, allows scientists to peer into the atmospheric structure of worlds dozens or even hundreds of light-years away, offering unprecedented access to their potential climates and habitability profiles. Further confirmation of the suspected molecules, including dimethyl sulfide, will come through continued use of Webb's mid-infrared spectrograph, an instrument designed to probe atmospheric layers with even more precision. This phase of the mission is critical, as it could yield insights into the thermal gradients, cloud dynamics, and potential greenhouse effects occurring within K2-18b's atmosphere. The broader goal is not merely to catalog the presence of familiar compounds, but to search for genuine biosignatures, chemical indicators that could plausibly result from living systems. In that regard, K2-18b stands at the forefront of the astrobiological frontier as one of the few exoplanets with evidence of both a potentially habitable environment and suggestive chemical markers. It occupies a special place in the catalogue of known worlds, and it is far from alone. The James Webb Space Telescope is rapidly transforming our ability to detect, characterize, and understand these alien worlds. Its instruments are capable not only of identifying the building blocks of life, but also of reconstructing the complex environmental narratives that shaped their evolution. Beyond the specific case of K2-18b, Webb has turned its gaze even deeper into the cosmos and unveiled another staggering revelation. Astronomers utilizing the telescope's infrared capabilities have identified complex organic molecules, aromatic hydrocarbons, in a galaxy so distant that its light began its journey to us over 12 billion years ago. These molecules, similar in structure to those found in fossil fuels and urban smog on Earth, represent the most ancient evidence yet of carbon-based chemistry in the universe. This galaxy, known as SPT 0418-47, formed when the universe was only about 10% of its current age, meaning that the presence of such complex molecules at this early epoch directly challenges existing cosmological models. These aren't simple compounds like water or carbon dioxide, they are large, intricate molecules consisting of dozens or hundreds of atoms arranged in ring-like structures capable of surviving harsh interstellar environments. The fact that these molecules emerged so soon after the Big Bang implies that the processes required for complex chemistry, and by extension the precursors to life, were already in motion far earlier than scientists had previously assumed. The implications of this discovery are profound. If aromatic hydrocarbons and other complex organics were already widespread less than 1.5 billion years after the birth of the universe, then the raw ingredients for life might have been scattered throughout the cosmos long before our own solar system even formed. This reframes our understanding of cosmic evolution and raises the possibility that the universe may be far more biochemically active than we ever dared to imagine. Webb's unprecedented resolution enables astronomers not just to detect the presence of these molecules, but to map their spatial distribution within distant galaxies. In the case of SPT 0418-47, researchers found that the molecules are not uniformly distributed, a puzzling detail that suggests local environmental factors may have influenced their formation or preservation. Even more astonishing is the fact that this ancient galaxy was already comparable in mass to the Milky Way and had produced quantities of carbon and oxygen rivaling those found in our own galactic neighborhood. Such early chemical richness contradicts earlier theories that predicted a slow, gradual buildup of heavy elements over cosmic time. Instead, it appears that certain galaxies matured rapidly, reaching levels of complexity once thought impossible for such a young universe. All of this has been made possible by the unique capabilities of the James Webb Space Telescope, whose instruments can detect faint infrared signals across vast stretches of space and time. By capturing the redshifted glow of ancient starlight filtered through alien atmospheres and interstellar clouds, Webb is opening an entirely new window into the story of creation itself. With each observation, the telescope is not only answering old questions but also posing new ones, questions that challenge the very foundations of our cosmological understanding. Could life have originated elsewhere in the universe long before Earth emerged as a blue oasis in space? Were the seeds of biology sown in galaxies whose light is only now reaching our eyes? As scientists continue to sift through the treasure trove of data provided by Webb, they are likely to uncover even more clues pointing toward the universality of life's essential ingredients. The future of space exploration now seems more promising and more complex than ever before. Webb is not just an observatory, it is a time machine, a chemical laboratory, and a philosophical catalyst all in one. With it, humanity is stepping deeper into the cosmic wilderness, tracing our origins across space and time. As the telescope continues to peer into the atmospheres of exoplanets like K2-18b, it will help scientists refine the parameters for habitability, distinguish between geological and biological sources of atmospheric compounds, and perhaps even identify worlds that are home to living organisms. The confirmation of dimethyl sulfide on another planet would represent a watershed moment in human history, a sign that Earth is not alone in fostering life. Similarly, the detection of complex organics in ancient galaxies underscores the fact that life's chemistry is not confined to one small corner of the universe. These twin discoveries, one looking outward at alien planets, the other backward into cosmic prehistory, together mark the beginning of a new era in space science, one defined by discovery, wonder, and the relentless pursuit of knowledge. As we venture into the unknown, armed with the tools of modern science and guided by curiosity, we are reminded of how small we are in the grand scheme, and yet how capable we are of uncovering the universe's deepest secrets. The cosmos, in all its vast complexity, is beginning to speak more clearly than ever before. All we need to do is listen. The James Webb Space Telescope continues to expand the horizons of what is scientifically possible, extending our gaze deeper into space and further back in time than any telescope before it. Every revelation it delivers is a piece in the grand cosmic puzzle, one that humanity has only just begun to solve. With each passing month, it becomes increasingly clear that Webb is not merely an instrument for observing the universe, it is a catalyst for redefining our place within it. The detection of carbon-based compounds on K2-18b, as well as the discovery of complex organic molecules in ancient galaxies, represents more than isolated scientific milestones. They are chapters in an evolving narrative that challenges our fundamental understanding of how life might emerge and where it might flourish. The concept of habitable exoplanets has long fascinated astronomers, but the tools to investigate them in detail have only recently come into maturity. Until now, most exoplanet studies were limited to indirect measurements, mass, radius, orbital distance, collected via transit photometry or radial velocity techniques. These methods provided a basic sketch of the planet's physical characteristics but fell short of painting a detailed picture. The arrival of Webb has changed everything. With its ability to perform transit spectroscopy in infrared wavelengths, Webb has enabled the direct observation of exoplanet atmospheres, effectively granting scientists the power to decode alien weather patterns, identify chemical interactions, and detect potential biosignatures from light years away. The case of K2-18b is particularly intriguing, not just because of what was found, but because of how it was found. The light emitted by its parent star passed through the planet's atmosphere during a transit, allowing molecules in that atmosphere to absorb specific wavelengths. The result is a fingerprint, a spectrum that scientists can analyze to determine the composition of gases present. Through this process, Webb revealed the presence of methane and carbon dioxide, two of the most important carbon-bearing molecules in the context of life. But it is the possible hint of dimethyl sulfide that stands as the crown jewel of this discovery. Although inconclusive at this stage, even the suggestion of DMS has lit a fire under the astronomical community. On Earth, DMS is a byproduct of life, mainly produced by ocean-dwelling plankton. Its presence in K2-18b's atmosphere would not only suggest the presence of life, it would imply that life in the oceanic environment of this distant world is producing chemicals just as it does here at home. Of course, scientists remain cautious. The detection of a molecule as complex as DMS from 120 light-years away is extraordinarily difficult, and there are numerous factors that could mimic its spectral signal: noise in the data, interference from stellar activity, or even unknown atmospheric chemistry could be at play. Yet the very fact that Webb can now detect compounds at this level of detail shows just how far planetary science has advanced. The planet itself remains a mystery in many ways. Despite being in the habitable zone, its large size and potential icy composition suggest that life, if it exists, would need to survive in high-pressure, possibly extreme environments. But as we've learned from studying Earth's own deep ocean ecosystems, where life thrives near hydrothermal vents and in complete darkness, biology can be astonishingly resilient. If similar extremophile organisms could exist on K2-18b, then life may not be the rare exception we once thought it to be, but rather a natural consequence of chemistry under the right conditions. The telescope's other major discovery, that of aromatic hydrocarbons in an ancient galaxy, has stirred a different kind of excitement, one rooted in the origins of life itself. These polycyclic aromatic hydrocarbons, or PAHs, are considered one of the building blocks of life because they contain complex arrangements of carbon atoms. On Earth, they are found in crude oil, coal, and even in the smoke from forest fires or urban pollution. Their detection in a galaxy that existed more than 12 billion years ago suggests that the raw materials for life were already being synthesized when the universe was still in its infancy. This challenges the long-standing view that life's essential compounds took billions of years to form and concentrate into planetary systems. Instead, it now appears that the universe began experimenting with organic chemistry relatively quickly after the Big Bang. That these molecules formed so early and in such abundance means that planets forming around early stars could have been seeded with life's precursors from the start. What makes this even more fascinating is the context in which these molecules were found. The galaxy SBT 0418-47 is not some chaotic, undeveloped cluster of stars. It is massive, mature, and chemically rich. Despite existing at a time when the universe was only a tenth of its current age, it had already formed a stellar population capable of producing significant amounts of carbon and oxygen. This suggests that galaxy evolution may proceed much more rapidly than previously believed, and that the early universe was a far more dynamic and fertile ground for life's chemistry than anyone imagined. Webb's ability to detect this level of complexity so far back in time gives astronomers new tools to investigate how galaxies formed, how stars aged, and how chemical diversity spread across the cosmos. It also opens the door to a new question: if complex molecules can form so early, is it possible that life itself, or at least its primitive precursors, might have originated more than once in the universe's early history? The presence of organic molecules, water vapor, and potentially habitable conditions in multiple systems suggests a galaxy teeming with possibilities. Webb is poised to observe hundreds, even thousands, of exoplanets in the coming years. Its instruments are designed to pick apart light at extremely fine resolutions, making it possible to distinguish between atmospheric components with great accuracy. By targeting planets in a habitable zone of nearby stars, particularly M dwarfs, which are cooler and more common than stars like our Sun, scientists are narrowing in on worlds where life might plausibly exist. Each new observation builds on the previous one, creating a compounding effect in our understanding of planetary atmospheres. And as the database of habitable zone planets grows, so too does our ability to classify them not just by size and orbit, but by their chemical makeup, energy balance, and potential habitability. In the future, Webb's findings will likely be complemented by upcoming missions such as the European Space Agency's Ariel mission, which aims to conduct a large-scale survey of exoplanet atmospheres, and NASA's Nancy Grace Roman Space Telescope, which will expand our ability to discover and characterize distant worlds. Combined, these observatories will offer a multidimensional view of the universe.